Chapter 9, Rotational Dynamics. This is a continuation of Chapter 8 where we saw rotational kinematics, where kinematics just means the study of motion. Dynamics is taking a look at the forces and behind those motions, right? We'll also see the rotational equivalent of forces. So this is continuing on and expanding our understanding of what we saw in chapters 4 and 5 on dynamics with forces. Now we're applying it to the rotational setting. So first, some contrast. Up to this point, we've mostly considered motion that is purely translational, where all points of an object travel on parallel paths. So this is shown with the gymnast on the trampoline, and they are jumping up, and they are staying upright and landing on the other side, right? Cool. And this is, like I said, mostly what we've assumed, where everything is just traveling as a single object. It may be following a parabolic path, but it is just translating. There's no rotation. Most general motion, though, is going to include a combination of that translational motion as well as the rotation that we introduced last chapter. So the gymnast, in reality, often will jump and spin in the air, right? So it's a little more complicated. We want to be able to study that as well. So we're deepening our study here. Now, in order for the gymnast to spin in the air, that's an angular acceleration. So let's think for a moment about what could cause that. Well, according to Newton's second law, once again, this equation pops up, a net force will cause an object to have an acceleration, F equals ma. Cool. What causes an object then to have an angular acceleration? It's not going to be exactly a net force. It's going to be a new topic known as torque. Let's take a closer look at what torque is. First, my favorite classic example is a door. You can try this out yourself. It works best if you have a really heavy door, because then it's more extreme. But if you go to open a door, you'll notice that it's easiest to open the door if you apply a force, if you grab the handle and push at the handle. It becomes harder if you push to the left as you get closer to this axis of rotation where the hinge of the door is. And it's really hard to open the door if you don't push on the handle at all. If you push towards the hinge, that's not going to accomplish much. So the torque is describing this force that causes a rotation. And we see here that it's not just the magnitude of the force, because in all three cases here, it's the same magnitude of force, but also where that force is applied and in what direction relative to this axis of rotation. Another way you could try this out or demonstrate it yourself is with a textbook, right? So if I want to open the front cover of my textbook, it is pretty easy to do that if I do it at the outer edge of the cover, right? This is not hard at all. It becomes significantly harder if instead I try to, instead of pushing at the outer edge, I try to push closer to the book cover, which is the axis of rotation. Oh, at this point, it is significantly more work for my finger, right? I could still open it, but it's significantly harder. You could try it with your pinky maybe. Yes, that is a workout, right? Pinky getting stronger. Similarly, if I want to open the cover of my book, it's best if I push directly perpendicular into that book cover. If I'm instead pushing towards the spine of the book, it's not doing a lot to open it, right? So I get the most effective result when I can just push perpendicular to that. So this introduces an idea of torque in action, where the ones where it's easier to open the door or the book cover are cases where you have more torque versus less torque. Before we can get to our actual definition of torque, though, I want to highlight a few definitions that will help us to understand this. So first, the axis of rotation. Axis of rotation we first saw last chapter, and that's the line at which about which all other points rotate. So with the doorway, it's our hinge, right? That's a vertical line that the entire door is rotating about. With my ruler being held by a pencil here, it can spin, and the axis of rotation is the pencil itself. The pencil looks like a point if you're looking at the front view, but it's actually a line, a line that everything else is rotating around. Right, so that's our axis of rotation. It's probably most familiar. Something that's very new is something called the line of action. The line of action tells you the direction of the force, and it extends in both directions from that force. So if our force is applied to the edge of the door here, the line of action would be anywhere along that line. So I could draw this out, and it could be something like this, right? Where it could be somewhere beyond the force, before the force, or anywhere in the force. This entire line is our line of action. So we could do that for a number of different ones, right? We could do it for the force over here. Maybe I'll get a slightly different color so it's a little bit easier to see the contrast. So again, the force here is up and down, so my line of action is just going to be straight up and down. Case C, notice my line of action is going to point in a very different direction. Instead of being up and down, which is the norm, we'll often deal with simple cases like that, I'd have to draw my line of action something like this, right? Where it's lined up with the force, but my line of action extends beyond and before. Now, why do we care about this line of action? Well, the reason we care about the line of action is because of something known as the lever arm. So the lever arm is the distance between the axis of rotation and the line of action. It's where the two meet at a 90-degree angle. It's also often called R perpendicular because of this 90-degree angle. So we have our axis of rotation over here, and it needs to meet the line of action at a perpendicular intersection. So if I get my straight line going again, if I go anywhere offset of this, I'm going to get a weird non-perpendicular line. But if I go right perpendicular to the force, then notice that is now an R perpendicular, and that is what my lever arm is. And we'll note the lever arm with an L. Notice for case B, because the line of action is also vertical, we're going to have a horizontal lever arm that goes from the axis of rotation to that perpendicular intersection point. But it's much shorter, right? Because the force is being applied much closer to the axis of rotation. Then finally for C, this one's perhaps the hardest to draw the lever arm for. So we draw the axis of rotation, and we need to figure out where we would have a perpendicular intersection. It wouldn't be over near the handle. That's going to be a tiny angle. So it looks like it would actually be somewhere like here, right? That looks about like a 90-degree angle, and it's a very small lever arm. That highlights how, even though the force is the same magnitude, it's not being very effective at rotating the door. Now that we've seen these definitions, we're much better prepared to officially define torque. Let's take a look. So torque is defined with a magnitude that is equal to the magnitude of the force times the lever arm. And what we'll use for torque is the Greek letter tau. So it's a curvy T as shown. I will often try to write it with an extra curve on top and a curve on the bottom to make it clear that it's not capital T like our period or our tension force. So you want to make sure you draw that carefully. This is a really great equation. So this is one that's going to pop up a lot. You do want to pay attention to it. And now we see why we care about that lever arm, because the size of the lever arm determines how much torque we have in terms of magnitude. Here are a few more examples of the lever arm drawn. Case A is just like our case A from before, where the line of action of the force is drawn and the lever arm is drawn from the axis of rotation to that force with that 90-degree angle between them. If the force is instead at some angle, the lever arm is also going to have to be angled upward to get that 90-degree intersection. And finally, if the force is directly at the axis of rotation, if you just apply a force right towards the hinge of the door, then in this case, the line of action is 0 because it passes through the axis of rotation. So that's not going to produce any torque. We get the largest amount of torque when we can apply a force that is perpendicular to the lever arm, that is as far away as possible and is pointed in such a way that it's nowhere towards the axis of rotation. That's probably a clear way to put that. Now this is just the magnitude of the torque. The torque is a vector quantity. Since it's a vector quantity, that means it does have a direction. The direction is just going to be positive or negative. So we'll say that the torque is positive when the force tends to produce a counterclockwise rotation about the axis. So counterclockwise rotation, CCW, is going to correspond to our positive torque. This is the same as what we saw in the angular section, where once again clocks are negative. If it's producing a clockwise rotation, that tells us it is a negative torque. And we can check that for the torque in cases A and B, which are non-zero torques. And we notice that this force is pushing up on the door. And so that looks like it's going to be a counterclockwise rotation if it actually rotates. So that would be a positive torque. Now, what about the unit of torque? Well, to figure out the unit of the torque, we can just look at what goes into the calculation. So we have force times lever arm. What is the SI unit for force? It's going to be newtons, right? And what about the unit of the lever arm? Lever arm's a distance. So what's our SI unit for distance? It's the meter. So the units of torque are just Newton meters. Newtons times meters. Note, this is technically the same unit breakdown as the joule, my favorite unit, but we don't use joules when talking about torque because torque is not energy, even though it happens to have the same units. So just note, this is not the same as the joule. We will always use Newton meters instead. All right. So this introduces the idea of torque. We'll check out an example of torque in the next video, so stick around.